So I'd like to thank the organizers for the kind invitation. I really wish I could be personally going back to LA. I miss it. But under this circumstance, I think the online workshop is the best thing we can have. And I'd like to thank the organizers and especially the IPAM people for their wonderful work. So today I will be talking about the incompressible porous media equation, and especially on the aspect of small scale formations as time goes to infinity. And this is the joint work with Sasha. So let me begin by introducing the incompressible porous media equation. Let's say that we are having some density of incompressible fluid in porous media. So let's just think about sand, for example. Throughout the talk, I'm going to set up the domain. So the problem is set up in 2D, either in R2 or the two-dimensional torus T2. Let's say that the fluid in the sand is incompressible, and let's denote the velocity field by u of xt. So then we know that, well, the evolution of the density is given by just this transport equation, and then due to the incompressibility, u has to have divergence free. Right. So for the Euler's equation, we know that it is essentially about the Newton's law says that the acceleration is proportional to the force. However, in porous media, things are quite different. In particular, that the Newton's law does not apply, that the force does not proportional to the acceleration, but rather that the force is directly proportional to the velocity itself. So this is called Darcy's law. And in particular, that's the Darcy's law in porous medium tells us that the velocity field u is proportional to the force, which is the right-hand side. So the proportionality constant is determined by the viscosity of the fluid and the permeability of the porous medium, which for simplicity, I'm going to set them both to be equal to 1. And the right-hand side is the force acting on the fluid. So there is this pressure term that is keeping the velocity field to be incompressible, and also that because the fluid is living in 2D, and then let's say that's the x2 direction downward is the direction of the gravity, and when the density is rho, it means that at each point the gravity is given this following force like this. Okay, and then the pressure term is responsible for keeping the velocity field to be incompressible. So in other words, the right-hand side can also be seen as the Leray projection of this desired velocity. So then you start with this velocity that is ideally that each particle wants to move in this direction. And however, that you do the Leray projection to make sure that the velocity field is incompressible. Okay, so for example, that if you're having a bunch of fluid here with positive density and negative density, then ideally that they just want to move downwards and upwards. However, that after the Leray projection, the actual velocity field will have certain correction just to make it divergence free. Right. In this case, u can actually be explicitly written in terms of the density itself. A simple calculation tells us that the Blowup law that is relating the velocity field and the density is given by the following. Which looks quite similar to the Blowup law for, let's say, the 2D Euler equation or the surface quasi-geostrophic equation. However, notice that there is a key difference that the two directions, x1 and x2, they are not equivalent here, right? Because the gravity is pointing downwards. And it turns out that in the Blowup law, there is this, the partial gradient in the x1 direction, horizontal direction. And then grad perp indicates that you take the gradient and then you rotate it for 90 degrees. So just to make it easier to intuitively understand what's happening, if we are having just a positive delta function hanging in there, then the velocity field that it creates, it's a incompressible velocity field. So it's in this direction, it's downwards and downwards. However, due to the incompressibility, that the other streamlines are circles that are passing through this delta function. And then the closer the distance is to this delta function, the stronger the velocity is. Okay, so this is intuitively what the Biot-Savart law looks like. And now we see that, well, we can just look at this transport equation with this velocity field, which makes it into an active scalar equation, where we have this scalar density rho that is transported by the velocity field u. Right. So we have seen quite a few other active scalar equations in this workshop. And now let me just use this little table to illustrate their similarity and their difference. In particular, that I'm going to compare three different active scalar equations, the 2D Euler equation in the vorticity form, and the 2D surface quasi-geostrophic equation, as well as the incompressible porous medium equation. So now first, the first line, let's look at their Biot-Savart law here. For 2D Euler, I'm writing the scalar as rho, but for 2D Euler, the scalar is actually the vorticity. For 2D Euler, we know that the velocity field is 1 degree more regular than the vorticity. Right. However, in the case for the SQG as well as the incompressible porous medium equation, the velocity fields are both at the same level of regularity as the scalar rho. However, that we can't just say that, well, these two porous and Biot-Savart law are about the same, because there is a significant difference. If we look at their Fourier symbol, so let's just look at each of these Biot-Savart law on the Fourier side, then of course, like in terms of the power of K, then SQG and the incompressible porous medium equation, they have the same power, while the 2D Euler have this extra -1 degree. However, that the thing that is the same for 2D Euler and SQG is that their Fourier symbols are odd functions of K, whereas that the Fourier symbol for the incompressible porous medium is an even function in K. Right. So for this difference, that we will be reflected in the sum of the local well-posedness results. And regarding the local well-posedness results, let's say throughout this talk, I'm going to be working with rather regular initial data that is in HS for S that is sufficiently large above certain threshold. I'm not going to talk about the more singular initial data such as vortex patch or things like that. So if we are having the initial condition in HS, then there is local well-posedness in all of these three equations. However, when it comes to the question that whether a smooth initial data remains smooth for all time, can there be a blow up in finite time? Then for 2D Euler, it has been known for almost a century since the work of Wolitner and Holder that the solutions are globally well-posed. However, for the SQG, it is a big open problem that whether the solution can develop a singularity, and the same thing is the case for the incompressible porous medium equation. So in the next slide, I will be reviewing in more details regarding the local well-posedness results for the incompressible porous medium equation. So from the work of Cordova, Gancedo, and Arrive, they proved the local well-posedness in HS, and for S that is bigger than a certain constant, I think 2 or something. And they also give various blow-up criteria. So some of the criteria are more similar to those of SQG. So for example, the BMO norm of the gradient of rho. And there are also some other blow-up criteria that they give Sobolev are more special to the incompressible porous medium equation, that are in terms of so namely one of the Blowup criteria says that if the level set doesn't oscillate too much, and if the Riesz transform of rho doesn't blow up, then the solution must remain regular. So that is for the incompressible porous medium equation itself. And if we modify the Biot-Savart law a little bit, so the IPM itself has beta equal to 0, but if we are increasing beta a little bit just to make the Biot-Savart law a bit more singular, then Friedlander, Gancedo, Sun, and Vicot shows that this Biot-Savart law is actually, this equation is actually ill-posed as soon as beta is bigger than 0. So notice that this is a sharp contrast with the SQG equation, because there you can make the Biot-Savart law to be even more singular, and then it's still locally well-posed in HS. But in here, they say that it's mainly because of the fact that the Biot-Savart law, the Fourier symbol, is even in K instead of odd, and that makes a big difference. So it is ill-posed as soon as beta is bigger than 0. However, the patch solution is locally well-posed for beta that is bigger than 0 up to 1/2. So these are regarding the local well-posedness versus local ill-posedness results. And regarding the global well-posedness results, for a large smooth initial data, the global well-posedness is open. And to the best of my knowledge, the only global well-posed results are the results when you look at this stratified steady state, where the lighter liquids are on top, the heavier liquids are on the bottom. So this is it is stable, and then this is a steady state in R2. And then Al-Jindi proved that if you slightly perturb this initial data in a HS for sufficiently large S, so this stratified data itself is living in R2, but the perturbation can either be, as long as it's small, can either be in R2, or you can also perturb it periodically. Then he proved that as time goes to infinity, there is global well-posedness for such initial data. And in addition, that it is, as time goes to infinity, it is converging to the stratified steady state with certain convergence rate. So his work concerns this steady state in the whole R2. And then when the steady state is just in a bounded strip that is periodic in X1, Castro, Cordoba, and Lear shows that, again, they look at the same stratified solution where the heavier liquids are on the bottom. And then they proved that under small perturbations, it remains globally in time regular. So these are, to our best knowledge, the only global well-posedness results. Regarding the question of whether it can blow up, so far there's no rigorous proof, and there are some numerical simulations by Cordoba and Gancedo and Rive. They show that the gradient of this density, the L infinity norm, can be growing as time goes to infinity. So they did extensive numerical simulation, and here I'm just stealing one picture from their paper. This is their initial condition, and here this direction is the x2 is the gravity direction, and so they did the simulation showing that as time increases, it tends to converge to some of the stratified solution, and then they zoom in to look at the level set. It turns out that in these places, the L infinity norm of the gradient is indeed increasing at some of the points, but they also compare it against their blow-up criteria that, and then they don't see the level sets gets too oscillating, and they don't see the Riesz transform blows up either. So, so they say that there are no evidence for finite time blow-up, although it looks like the L infinity norm is growing. So together with Sasha, in our work, we are going to assume that there is a global in time solution because we have no idea how to either show the global regularity or prove finite time blowup. So assuming a global in time solution, our goal is to rigorously justify the fact that the gradient can indeed be growing to infinity as time goes to infinity. So before I talk about our problem setting, let me first go over some of the previous results on the small scale formation for the 2D Euler and SQG equation. So for 2D Euler equation, there has been extensively literature on the growth of the gradient of the vorticity. It started with this earlier work, and so most of the more recent work, starting from this Bahuri-Shimon work, they all are based on the idea that the 2D Euler equation has a steady state. Well, it's not smooth, it's actually a discontinuous steady state that has a hyperbolic flow structure in the sense that in this torus, if we put this omega to be +1, +1, -1, -1, this odd structure, then this structure will remain for all the time. This is a steady state. And if we zoom in this 0 point, we will see that, well, the trajectories are approaching each other double exponentially in time. Of course, this doesn't mean anything about the dynamical solution, but one can construct the dynamical solution that are approximating these dynamics in some way to make sure that's there's for smooth initial condition, that's the trajectories are approaching each other. So these ideas are used in the work of Denisov, and then Kiselev and Schwarak prove that in the disk there can be double exponential growth, which is sharp. And then Zlatosh deals with the case in the torus, and then he proved that there can be exponential growth. And more recently, for the SQG equation, Kiselev and He proved that assuming that the solution remain regular for all time, there can be exponential growth of the gradient, using a similar idea where they also consider the initial data to be starting close, very close to this discontinuous steady state. So these are the ideas for proving the growth in the 2D Euler and the SQG. However, when it comes to the incompressible porous medium equation, there are several difficulties. The first one is that notice that it doesn't have the same symmetry as Euler and SQG, namely that the odd symmetry will not be preserved, but rather that what is preserved in time is actually the odd even symmetry. But this is rather a minor issue. So the symmetry doesn't really matter here. But what is the more essential difficulty is that in Euler, there are plenty of steady states where, so there are these, when one follow the trajectories can get close to, can approach each other as time goes to infinity. Right. However, unfortunately, for the incompressible porous medium equation, one can easily check that the only steady states are all these boring ones. They're all stratified where the density is only a function of x2. And as a result, no matter what is this density in the x2 function, one can just directly see from the Biot-Savart law that once you take the x1 partial derivative, well, u is 0 for free. Right. So that means that it is essentially impossible to use this idea that we start from some steady state and then do a variation and hope the gradient will grow. So that is the reason that all the previous ideas could not be adapted to the incompressible porous medium equation. However, we realize that thanks to the special structure of the incompressible porous medium equation, there is actually a completely different approach that allows us to get the infinite in time growth. And it's by actually quite simple argument. So this is based on the forthcoming joint work with Sasha, namely that we were able to find smooth initial data in the torus. And so such that, again, assuming that we have a smooth solution for all the time, then if we are looking at the H beta norm of the rho partial x1 derivative, then the negative sum power of this norm is integrable in time. Okay, and we know that for anything that is integrable in time, it means that it needs to have certain decay in time, right? At least in the average sense. And therefore, if this quantity itself gets small, it means that the norm itself must be unbounded, getting large with certain rate in time. So here this norm started with beta bigger than -1/2. So translated to the norm of rho itself, it means that starting from the h1/2 norm of rho, for anything that is bigger than 1/2, we will see that this norm of rho will become unbounded as time goes to infinity. And so the lim sup of this is infinity, and this power depends on how big beta is. So meaning that rho has infinite time growth in all these Sobolev spaces. So let me briefly discuss the idea of the proof, which is actually very short. So we set up our initial data such that it has this, it is odd in x2, but it's even in x1 variable. And and then we made rho to be 0 on these boundaries, and rho is bigger than, it's a smooth function that is bigger than 0, so it's somewhere in this square. Okay, and then we know that this structure will remain true for all the time. Whatever that is inside the square cannot escape it. And the main tool of our proof is the monotonicity of the potential energy, which is this integral of rho times the height times dx. And first notice that because the things are just transported by an incompressible flow, the L infinity norm is invariant in time, which means that we have an a priori bound of this potential energy. It's uniformly bounded by some constant for all the time. And then a quick computation using the periodicity and the oddness in x2 will give us that, well, the potential energy is actually dropping in time, which is, which the computation is right here at the end. Well, this is not surprising given that the whole incompressible porous medium equation is driven by that the heavier thing tends to go down, the lighter things tends to go up. So it means that this potential energy is monotone decreasing in time. And then because we know that E is uniformly bounded, it means that the time derivative of E is integrable. Right? So if we call this quantity to be delta, then we are having that, well, delta is a quantity that is integrable for all the time, assuming the solution exists globally. And therefore, for large time, we know that delta has to get small, right? At least on the average sense, delta has to get small in some way. And that means partial x1 of rho will have its h-1 norm to be tiny for a large time. And now we just want to translate that into, well, does that imply that the Sobolev norm, maybe some positive or some bigger than certain extent Sobolev norm of rho must be huge? Right? So why is that true? Well, it's because thanks to our setting, this even odd setting and our choice of initial data, rho will be equal to 0 all the time on this vertical line. So if we zoom up this little square here, then at all the we know that rho is equal to 0 on the left boundary, and rho is, well, having certain distribution, right? The distribution is deforming, but the distribution itself is remain unchanged. Then an easy argument will tell us that, well, it means that for all the time, we know that the integral in this little square of the partial x1 derivative rho cannot get too small. So it is bounded below by some uniform constant, only depending on rho 0. And therefore, the L2 norm of partial x1 rho.
Yeah, maybe another couple of minutes.
Yes, I'm almost there. Thank you. So the L2 norm is bounded below, which means, well, if the H minus 1 norm is small, then the H1 norm has to be huge, right? So this is the quite simple argument that tells us that anything bigger than the H1 norm will grow to infinity. A slightly more sophisticated argument, if we look more carefully on the Fourier side, we can actually get that anything bigger than the H minus 1/2 norm will be growing. So that is like if we are looking at these type of initial data, then it's the H beta norm for beta bigger than -1/2 can grow to infinity. We are also able to show that, well, even if our initial data is stratified, we call it the layer solution, then there are also initial data that can lead to growth. So let me just briefly show you this picture here. So let's say that this is our domain torus, and it again is odd in x2. So let me just show you what happens for between this 0 to pi. So for any of these layered initial data, there exists a unique stratified steady state that is reachable from this data due to its topological constraint. Right, which is that, well, just take any level set, and then there is a unique position for this level set where the area remain unchanged. Right, so and then let's call that stratified state to be rho s. And we were able to show that, well, if initially the energy of rho 0 is already strictly lower than rho s, then this remains true for all time, which means rho 0 can never get too close to rho s, right? So their distance must be separated by certain extent. And therefore, which means that actually rho of t can never get too close to any stratified state. And using that argument, again, we are having that, well, the L1 norm of this partial x1 norm of rho can't get too small, and therefore this leads to the growth as time goes to infinity of this H1 norm or anything higher. So that is just a very quick argument, a completely different argument from all the previous results that shows the infinite in time growth of the incompressible porous medium equation. So let me just stop here and thank you for your attention.